Okay, welcome to part 3. I'm glad that you have all survived. Can you hear me at the back okay? Is that right? Yeah, perfect. Okay, so who of you has tried to scale one of your applications? Okay, a bunch of you. How successful have you been? Honestly? Yeah, okay. Alright, so what are the basic problems with scaling? Well, your operations per second go up, your storage needs go up, you have more capacity because you've got more data, you've got more IOs per second because there's more data, there's more people using it, and your complexity goes up. You know, you start putting caching and other things in there to deal with the complexity. So this is kind of how you scale up the model at the moment, and this is probably what you're doing, which is you start off here and you try and scale vertically, which means you spend lots of dollars and get very little additional throughput. And so scaling vertically is very expensive and more or less impossible to do in the cloud if you're using EC2. The biggest EC2 machine is not very big. So how do you solve this problem? Well, this is how we do it in MongoDB. We have inbuilt into MongoDB technology called sharding. And sharding is very, very simple. It's essentially a range-based partition scheme. So if I was doing, let's say this is address book data. So these are people's surnames, A through Z. And let's say we've got 300 gig of that data. You know, that's probably everybody in the known universe, but let's leave that to one side. What I can do with sharding is that if this machine is out of capacity, if it's out of CPU, it's out of memory, it's paging, it's swapping, you run out of IOPS. Well, what you can do is you can use sharding to divide up this data into two sets. So I've taken this, my address book, and now I've divided it into two halves. So this is A through M here, and this is N through Z here. And I've taken my 300 gigabytes of data, and I've divided it in half, which means there's 150 gigabytes on each machine. Okay? And so I can keep on adding more nodes into this cluster. So I've now got 3 nodes. I've now got that 300 gigabytes of data spread across 3 machines. Okay? Which now means that this machine that was out of capacity has now got much more availability of memory, RAM, IO, and CPU because we've taken the data and spread it across the machines. Okay? And so another way of thinking about what sharding is doing, and we'll talk about the details of this in a second, and the great thing about sharding in MongoDB is that it's automatic. You don't have to take any downtime, and you don't have to change any code. So that means that once you've got your code deployed, the operations guys can add more capacity into the cluster online without any downtime. Okay, so that means that if your feature or your product is wildly successful, as a developer, you can go to bed every night and rest peacefully. Because you know, in terms of horizontal scalability, you can simply just add more capacity to the cluster as and when you need it. Now, another way of thinking about sharding is that it's also a caching solution. Okay, so again, I've got my data. I have got 300 gigs of data. I've got 96 gig of RAM, which means that I've got a 3-to-1 ratio of data to memory. Okay, so there's a 1 in 3 chance that that data is going to be in memory. There's a 2 in 3 chance it's going to be on disk. Okay. Now, if I take that same set of data and I now shard it across 3 machines, I've still got 300 gig of data. Each one of these machines has got 96 gig of memory. But now for each machine, it's got a 1-to-1 ratio of memory to data. Okay? So what essentially I've done here is I've put all my data into memory. Okay? Now I've got a customer out in Israel who they started off with 3 shards, and they're up to, last time I checked, 260 shards. And they have a voice over IP application. So voice over IP is very latency sensitive. And so what they do is they ensure that they have enough shards to maintain their entire data set in memory. Now they've got 260 machines, times 96 gig of memory. That's several terabytes of memory. They have allocated, this is all running in EC2, to keep their entire data set into memory. So with this kind of sharding technology, you can start doing some very creative things. Now, the other built-in technology into Mongo is replication. And so we have inbuilt-in replication. So if I take my address book again, and then I make 3 copies of it, my footprint is now 600 gigabytes because I've got 3 identical copies. But having 3 identical copies has got some very useful features. I could lose any one of these features, any one of these copies, and I've still got other copies available that I can fail over to. So this makes my data highly available because I have multiple copies. But it also means that I could actually use these multiple copies for many different purposes. So I could use this for my backups. I run my backups off this copy of data. Or I spread my read load across all of these copies of data. So you can use the multiple copies of data for a number of solutions. So if we go and let's talk about the internals of sharding. Okay, so there's a whole bunch. I apologize. This got one of the few times in my life I've ever used animations, and I've got a bit carried away. Okay, so let's have a look at our problem again. We've got a large data set here, and let's say this is usernames of a system. So what we have in MongoDB is we describe all these data as essentially a set of ranges. And what we do is we divide these ranges into what we call chunks. Okay? And this is the same thing as Hadoop and a number of other technologies do. And so right now, so you can configure this, but the default size of a chunk is 64 megabytes. So that's describing 64 megabytes worth of data. And so what we then do is essentially what we've got here on our usernames is this chunk is describing D, this chunk is describing F, this is Z, S, G, and so on and so forth. And we can now take these ranges of data and we can now spread these across each one of our nodes in the system. So let's just do that now. Okay. So we map these ranges, and therefore we map the data across all of these nodes. Okay. So node 1 has got Z, C, A, and S, and so on and so forth. Okay. So that's how we partition the data across all of that data, or all of those physical machines. Okay, so the next step is, well, what happens if I've run out of capacity and I want to add a new shard in? Well, essentially, the goal of the system is to hit equilibrium, i.e. to ensure that the data is evenly spread across all of the nodes. Okay, so you can add a node dynamically, you can also remove a node dynamically as well, and what we've got to do is distribute the data across the system. So how does that work? Well, essentially what we do is we take data from the existing shards and then we relocate that data over to our new shard. Okay? So we've taken W, Y, B, and X from those other nodes and we've placed it here. Now from your application perspective, you are reading and writing data. And the key thing that we do during this relocation of data is that we make the data's location transparent to you, your application code. So as this data is moving across the system, your code is unaware that is happening. So that's that. If you are making changes to, say, data in this B range, what MongoDB is doing is, as it's copying the data across, it's keeping a list of those changes that have been made, and then we'll reapply it to this end to ensure that these chunks are identical before the relocation has finished. So this is happening online in real time as you're reading and writing data. So how does reads and writes occur? So there's a key process, there's a MongoS process, which acts like a sort of router or a switching process. So if I want to write to the key of Z, well, where is Z? Z is over here. Okay. So what happens is we take this write request, and because we've mapped the key ranges to particular shards, it means that we can actually route this write request directly to this one node. We don't have to take that write request and send it to all nodes, because we know that Z is here. Okay? So that command is always routed. So what happens if you are doing a read? Oh, so we'll do a split first, sorry. So if you've reached this 64 megabyte limit, let's say Z was a very popular name in the Czech Republic. What will happen is, if this starts describing more than 64 megabytes of data, we can actually now split this range. Okay? And so what we end up with is this Z is now split into two chunks, Z1 and Z2. Okay? They now describe 32 meg of data, and so we can now insert into both of those. Okay? So that now means that we then relocate that data. So that split occurs within this node. We've not had to move any data at this stage. We could just split that key range so it's a finer granularity. So just imagine the tree is getting kind of deeper and deeper, like a B tree index would do. So if we can now come to execute a query, second part here, again we'll rebalance. And so what we've done here is that we can now rebalance these smaller chunks across the system. Okay, so as any one of these key ranges breaks down into smaller pieces, we can then migrate the data between the cluster. Okay? Questions so far? Does it make any sense at all? Okay, I may have blinded you all by science. Okay, so the next part is what happens to a read. So your application is executing a query. What happens with that? Well, so we're reading Xavier. Okay, we know that the X range is over here, which means again we can take this read request and instead of scatter gathering it across the whole cluster, we can direct this query to where the X range exists. Okay, so again this is a very scalable solution because we can take our queries or write requests and send them to the right part of the cluster. Now, let's say we do a range query. Range query is more exciting. So let's say we wanted to do a read of the values of t through x. Well, again, we can route the query to just the right parts of the cluster. Okay? So we know that u, t, v, w, and x exist on these parts of the cluster. And so we'll take this query and then just send parts of the query to the parts of the cluster that contain that data. As you can see here, this node did not contain any of those data ranges, and so it never sees that query. Again, this is transparent to your application. Yep, so as the data moves around, or you add more capacity to the cluster, you have more shards, your application code remains identical. This routing process here will take care of the data in its physical location. Okay? So this is a really shorter version. So the idea is that scaling is going to be simple, right? The key thing is you add capacity before you need it. So with any kind of horizontal scalable solution, if you're already at 98% utilization, sharding is not free. We have to read the data in order to move the data across the system. Okay? So you need to have the right kind of monitoring tools in place. So if you use Nagios or Cacti or Zabbix, any of those open source frameworks, there's a plugin for that. 10gen itself has the MongoDB monitoring service, MMS. You can download and use an agent for free, and that will give you all of these kind of key performance indicators. But you kind of want to add capacity into your cluster before you need it. As we talked about, the system will automatically rebalances your data. Okay, so that means if you have an uneven distribution of keys, like the letter A is more popular than the letter W, then the system is automatically going to divide those key ranges into smaller chunks and then relocate that through the cluster. You don't need any downtime and capacity, and most importantly, you don't need to change any code. Question?
Where do you store the index?
Where does the index get stored? Well, let me go back to a picture. So, where does the index get stored? Well, the index actually gets stored on each MongoDB cluster. Right? So, when you create the index command is sent to each shard, and the shard then builds the index for those values that are present in those shards. Okay, so again, it's very efficient, and that's true of not only just the primary key index, but any index on any other attribute value.
Okay, thanks.
So there is some kind of super index in the, you said, row there?
Yes.
It must be also something like index that tells what shard is being used.
Yes, so if I was to look at I'm presuming... Okay, so if I was to look at a physical deployment, what we have here is your application. Can you see this all right in the back? No? Don't worry. Well, this is not a particularly great pen. Right, so I'm going to do the best I can. Here is your application. Nice fluffy cloud. We have our 3 shards. And this pen really is rubbish. Okay. Let's have a bit more luck. Great. Okay, here's shard number 1, here's shard number 2, here is shard number 3. Okay. So what we have is our MongoDB process. And so this is a switch, like a software switch or a routing process. And so the routing process has access to our configuration DBs. And the configuration DBs simply describe these key ranges. Okay, so just imagine that this is just a tree structure. And then it has a mapping to which shard it is. So this will say this is in shard number 1, this is in shard number 2, this is in shard number 3, and so on and so forth. So that means when your application executes a query, you do a db.find, db.posts.find, and we're doing a squiggle of author is her gay. Forgive my writing. What we're looking at here is that we see this is the predicate. Okay. Now, if these key ranges described author, essentially we can look up in the key range, look up in this tree where H is mapped to. You can say, look, H is actually mapped to shard number 1. And so what the MongoDB process does is it then takes that query and routes the query over to this shard. And that shard then goes and executes that query on behalf. And then the data is magically returned back up to the MongoDB process, up to your application. Now, if that was a range query, then there may be multiple queries that are executed on multiple shards. The MongoDB process now does the sort merge of those results to present back to the application. So this is why the application is unaware of how many shards there are in the system, because the MongoDB is dealing with not only with the routing, but also with the sorting of them and the merging. Now, clearly the most efficient queries are those that are routed. So if you are using the shard key that you use to distribute the data, that's always going to be routed. You can still do a query on anything other than the shard key, on some other attribute, but that will mean that because it's not the shard key, it does not know where that data resides, which means that you have to do a scatter gather across all of the shards, so they all execute the query, and then the results are pulled back together in the MongoS to send back. Okay? So whilst MongoDB is scalable, it doesn't necessarily mean you have your applications will scale. So you have to look at your query patterns and your shard key to ensure that as you add capacity, you get more throughput. If you are not using the shard key in your application, it means is as you add more capacity, all those nodes are equally busy because they see every query. Because every query would have to therefore be pushed to every shard. So it's very critical, and there's a, I could talk for hours on choosing the shard key. But picking the shard key is key to get this horizontal scalability.
And can the shard key reflect more than one index?
So the shard key can be a compound key, so you can put multiple things in there. Absolutely.
So can you somehow, like, have MongoS running on multiple nodes?
Absolutely. So you can have as many MongoS's as you need. The typical deployment pattern would be to have the MongoS running where the application server is running. So the application server connects to MongoS over localhost, and then the MongoS talks to the cluster.
Yeah,
and an alternative to that is that you have a farm of MongoS's with a load balancer with sticky sessions in front of it.
Yeah, and the configuration DB, that's, what is it? Is it like a normal DB? Or?
Yeah, so the configuration DB simply contains this metadata. So typically it's 20, 30 megabytes of data, it's a small amount of data. These are regular MongoDB processes, and in a production system you'd have 3 of those. And this is to give you the ability that if you lose one of the config DBs, you've still got that metadata available. If you lose all of the config DBs, then the MongoS processes keep a cached copy. But if you start a new MongoS process, there's nothing to read from, so it does not know where the data is. Now, this leads to some interesting things that you should not do, which is, let's say you went and deleted all your config DBs, and I had a customer who did this. I won't explain why, but they thought it was a good idea to go and delete the config DBs. All of a sudden, all of the queries in the application were returning no data. Right? Because without this metadata, we don't know where the data is located. And they hadn't backed up their config DBs. And so we had to reconstruct the config DBs from the data instances. And that took something like 14 hours to go figure out where all the data was, because they had, their cluster at that time was about 90 nodes. So I should put that in the slide. Don't delete your config database and do back it up. Because that will give you a whole bunch of pain.
Why is it possible to delete config DB?
Well, it's a bit like, I have a basic philosophy which is on a new Linux or Unix installation is that you remove the rm command. If you remove the rm command, then you can't do stupid things. MV is bad enough, RM is really bad. So sometimes I'll alias RM to be MV. But how does it happen? People just delete files. You can shut processes down, you can delete files, you can turn off machines. And this is a fairly serious concern, which is you're running in something like EC2, but there's no guarantees on machine availability. If you lose a machine, you need to have multiple copies of the data around to allow for the high availability. So the basic philosophy of MongoDB is you have lots of processes, you have lots of copies, because any part of that system is unreliable. If you assume everything is unreliable, then everything will break, and therefore you have the redundancy and the inbuilt availability. Okay. Any other questions on this? Yep.
What happens if one of the data node crash or just don't respond for queries?
Great question. So I didn't talk much about replication. So typically behind a shard, so think a shard is a subset of data. Behind a shard, what you'll have is a replica set. Okay? And so let's just talk a little bit about replication in this corner. Oh God, the blue's not coming off. Well, you saw me test the blue pen, right? Yeah, well. Alright. Pick this up. Here we go. This is what I'm looking for. Oh, and we actually have a whole bunch of things to give away. Apparently we've got some goodies from our friends at Google, and I bought a whole bunch of MongoDB stickers and things like that. So apparently I'm supposed to give away stuff to the best questions of the day. Obviously the organisers don't count.
Crap.
Alright, so how does replication work? So the key thing about replication is what are the things that you really care about? The first is so you just do this to see how I'd survive. Okay. Alright, I think this is dry enough now. Okay, what do you really care about? You care about data protection. Okay, and you also care about high availability. Okay, so how do we deal with that? Now, if you've used replication, master-slave replication in MySQL or even in Oracle, God forbid, because if you're doing it in Oracle, you've probably spent 5 weeks setting it up and it still doesn't work. All of those systems are essentially master-slave, which means that it's great. You've got all these slaves. Here is my master, and here is my slave, and I can chain slaves, and this is really cool. When my master dies, what happens? Well, you get a page at 3 o'clock in the morning, and your boss shouting at you, and then you have to figure out promoting one of these slaves to be the new master. Okay? We think that's an inherently bad idea. So we have what we call a technology called replica sets. You see this all right at the back?
You can use the violet marker.
It's violet better. Oh, ooh. Okay. Can you see me at the back? All right. So, first of all, let's say this is member A, B, and C. Right, we satisfy our data protection requirement because we've now got 3 copies of the data. How do we satisfy our high availability? Well, let's start off with this is the primary. Okay? So the actual topology would look like this in MongoDB. Oops, don't use the green arrow. So this is a secondary, this is the primary, this is a secondary, and this is a secondary. So the secondaries are doing asynchronous replication, which means that they are reading from the primary, they're pulling all that changed data down, and then applying it to a secondary. Okay? So at the point where this primary fails, the machine is shut down, either deliberately or accidentally. It gets rebooted, something happens, the disk drive gets set on fire by a frustrated admin. Your primary dies at this point. Well, the surviving members of this set, so these are the surviving members, they have a heartbeat that goes around the cluster, and they'll look for so many misses in a certain period of time. And the 2 of them will decide that A has disappeared, and they'll do a quorum-based election. And so what will happen is they'll decide which node has the most up-to-date information. Let's say it's C. And so C now gets promoted to primary. Okay? And this set will automatically reconfigure itself, so B will now pull data from C. Now, from your application perspective during this, this event, what you'll see is that you'll try and do a write, and that write will get an exception, an IO exception, because there may not have been a primary you could have written to. If you're executing queries, the queries will still work during this election process. So at this point, life is good. We've got a primary we can now write to. We've got a secondary that's automatically resyncing itself. Well, let's say somebody just rebooted this machine. This machine comes back and it goes into a recovery mode. Let's say it was down for 60 minutes as you replaced a disk drive or added some more RAM in or figured out where this machine was in this sea of boxes in the data center. And so it goes into recovery mode. It figures out who the new primary is, which is C, and then it'll start reading that 60 minutes worth of data down. And so it'll automatically recover and catch up itself, and once it's caught up, then it just becomes a regular secondary in the system. Okay, so that's how we deal with high availability. Now, there are many different types of topology you can set yourself up with. So this is just a simple 3 node, but you can go 3, 5, 7, up to I think the current limit is 16. But you can also spread these nodes across data centers or availability zones in EC2, for example. So, for example, if we go and extend the set, and we put D and E, we could actually put this in data center 2 and these 3 in data center 1. Okay? So now I've put data across 2 data centers, which means that if this data center fails, I've still got these viable sets of data. Now, if my primary data center fails here, what do you think happens?
Election.
An election is called. Okay, but what happens to these 2 guys here? Well, the key thing about an election in MongoDB, it's like a parliamentary election. There has to be a majority. So these 2 guys, the set is 5, they only see 2/5 of the set. Okay? And so what these guys will do is these will go into a read-only mode because a majority does not exist. So this could be simply that you lost this data center or you lost connectivity between data centers. So it always works on a majority basis. So if you wanted to do automatic failover, what you probably want to do is you want to add another member here, of F, and then in a separate data center, you can put, that's G, we can put what we call an arbiter process. Okay. Now, an arbiter does not have a copy of the data, but it gets to vote in an election. Okay? So that means that if I now lose this data center, can we do automatic failover to this data center? Well, we can because we've got 1, 2, 3, 4. Okay? We've got 4 out of 7. So that means we have a majority. Okay? So depending on what you need for the reliability of your data, you can set up different topologies to allow for failover within a data center, automatic failover across data centers. It really comes down to what are the business requirements for your data and also how much money you have. Because obviously you've got multiple data centers, you've got the cost of all this extra equipment. Can that make sense?
Could you somehow mark any collection which is important for the business, critical for the application life, and replicate it more times than another? Just on the level of collection, not whole database.
Well, so the way that replication works is that we replicate everything in the database.
Yeah, but could I replicate one collection more? It's not.
Well, we have a slightly different view on that, which is we think you want to keep copies of all your data. Yeah, losing some of your data, some is not good because then you're left with some of your data, and what do you do? So if we think about durability, so if I do an RDBMS, so if we have memory of the server, we then have the journal or the redo log, we then have disk. Okay, so when you issue a commit in a relational database, a relational database guarantees that you've at least hit the journal file before that commit is acknowledged. Okay, so you do a commit, you wait for some time, the data hits disk, and then you know it's at least in the journal or the redo log, which means that the database process crashes, that data can be recovered by rereading and reapplying the journal. Now, that doesn't really matter whether you're writing log data or stock prices or credit card transactions. A relational database treats the durability of all data the same. Now, we believe that not all data is created equal. Some data you want less durability, some data you want more durability. So, if you say W equals 1, and this is a write option, but essentially what that means is the data has at least got to be acknowledged and be in memory. There's no guarantee that it's on disk, but you've acknowledged it at least in memory. You can say journal equals true, which says at least the data is in the journal. Okay, so you've got equivalent durability as a relational database. What I can also say is, if this is my secondary, I can say W equals 2, which means not only it is in memory, it's written to the journal, it's written to disk, but it's actually on a secondary member as well. Okay? Now, this secondary member you can now extend. So there are semantics that say, look, when I do this write, only acknowledge this write if it's in both of my data centers. Okay, so you can extend this durability to give you much more higher levels of durability than you would do in a relational database. You can also have it so you've got less durability than a relational database. The key thing here is, as the application developers, you get to choose. Okay, so it's not one size fits all, it's like choose the durability in relation to the data. Now, coming back to your question about, do I want to replicate more copies of this? This is essentially how you can do this. You can say, look, this write is very important. It's a credit card transaction. Let's make sure at least it's in both data centers before I acknowledge that write. And so we think of durability of data differently from the replication of data. The durability of data is controlled by the application developer. The replication of the data is controlled by the operations team. Because they understand the physical deployment and the needs from the business perspective. The application developers understand how little they love their data or how much they love their data. Make sense?
Another question. When you know that, yeah, that's the main motivation, but thank you. Is it a big deal? Possibly, yeah.
You can trade prizes afterwards.
When you know that any data in any collections, credit card numbers. Yep. Credit card number of American customer couldn't leave USA, the data center from USA. What you will do when you are unable to replicate just some collections? Will split it to multiple databases, or?
Yes, so we have a feature that's coming in our 2.2 release, which is going to be available summertime, so anytime soon, called geo-sharding. And what you can do in geo-sharding is two things. So there's two general problems that people have of distributing data across lots of machines. One is that they want to have locality. They want to put data close to where it needs to be. So for example, they want to put Asia data in an Asia data center, US data in a US data center. But they also, for example in Germany, there's very stringent rules about data moving across physical borders. And so with those same rules in GeoShardy, you can say, look, this data not only is located within this boundary, but actually can't be moved outside that boundary. So you can start building those rules up for the geolocation of data. Make sense? Okay. Other questions?
Just to my original question, when you have set up the cluster of a few data nodes.
Yes, your question was a long, long time ago, wasn't
Yeah,
it?
and one of the nodes just crashed or disappeared.
Yes.
And what's the application do?
So, it comes down to this problem, which is if this was your primary, your application by default is doing all of the reads and all of the writes to the primary node. Okay? If the primary dies, we've already talked about how the failover occurs, and so one of the surviving members will be re-elected as primary. From your application point of view, what you'll see is you'll do a write operation, and that write may fail. You might get an I/O exception, you may get an exception back through the Java stack. And so you then have a choice, which is you either wait and then reapply that write, or you throw a message back to the user if it's an interactive application to say, please try again later.
Okay, so basically one of the, because this is like failover, but what we are talking about before was the cluster, like a few nodes containing different data sets.
Right, but behind each shard you have a replica set that protects the data and makes it highly available. Okay, so in this node here, which has got T, F and E, we'll have a replica set of 3 or 5 or 7 nodes to protect this data. And so you'll have automatic failover within that shard, i.e. that key range.
Okay, and can I ask about like the, you talk about the moving chunks between the nodes.
Yes.
What guarantee us that there is no some performance penalty or something? Like what's your magic?
There is no magic here, which is, well, there is magic, but we're dealing with physics, right? So the physics is that we've got disks that spin, we've got network cards, and we've got CPU. So to relocate this G chunk from this node to this node, what do we have to do? First of all, we have to read all the data in, so that we can then send it across the network to this node, or this shard, which then will insert all of that data. So there's a read that's going on here, there is inserts going on here, there's also index maintenance that's going on here, and when the data has finally been relocated, there's a delete that occurs here, which is going to be index maintenance. So there is load that is applied to the cluster as that relocation occurs. That load is applied as a background thread. So all of the interactive operations that are coming in through your application will take higher priority than the relocation of data.
Okay, and it's some kind of schedule or time basis, or like when the MongoDB decides to move one chunk to another?
So the question is when does this occur? So by default, it's running 24/7.
Okay.
You can actually set up the balancing process to run on a schedule. You could say, just run from midnight to 5 AM every day. So you can actually sort of either keep it running just on a schedule basis or just turn it off completely. So those are options as well. Okay. And I think you win a t-shirt for putting up with not getting 3 hours of Oops. Almost said go to your camera. Okay. Other questions? Does any of this make any sense? Does this kind of make you want to kind of like download and try this? Don't know if I get past this slide. Because you can download it. And so the reason why we love open source is what it's allowed us to do is get from an idea that we had back in 2007 into last year we had 1.5 million downloads of the product. We get about 130, 140,000 downloads a month. What this has allowed us to do is get the products into lots of people's hands, to try it out, to figure out what works for them and what doesn't work for them. But also allows us to understand from, instead of like sitting in a dark room somewhere dreaming up features, we get very much driven by the community that needs new features built. So for example, we have geospatial indexing. We built that because our friends at Foursquare said, we love your database, but we still have to use Postgres because we do all of our geo searches in Postgres. And we said, well, kind of what searches are you doing? And they said, well, it's like 2. It's a bounded box and it's a within. And they said, well, we don't think that's going to take very long for us to code. And so our CTO coded that over one weekend. And you know, after some rigorous testing by Foursquare, they managed to basically move off Postgres and do all their geo searches in MongoDB. And it's very much how we want to carry on developing. And it's one of the reasons we do things like this, which is it's as much to kind of get you excited and interested in it, but also to get your feedback and figure out what you guys are building and what features of a database you need in order to be successful in your mission. And we see our mission as building all the infrastructure, and you get to have all the fun writing all the applications. But we don't necessarily know all the applications you're writing. And so please do download it. If you have any issues, please send me an email. There are a bunch of community forums. So there's a Google Groups called MongoDB User where you can go ask questions. All of our engineers sit there and we'll respond to them, so you get an answer from the 10-gen engineer. There are a bunch of events that go on. We do conferences. The nearest ones to you guys are in Berlin and in Munich. So Munich's coming up the week after Oktoberfest. So if you can schedule drinking beer followed by a MongoDB conference, then that may be an option for you as well. I think that's probably all I've got.
Okay, cool.
Thank you very much. I have no idea where we're going for beer.
It's